Hey everyone, and welcome to today's explainer. Today, we're building a high-yield conceptual map of the D and F block elements. If you're prepping for competitive exams like the JEE or NEET, you already know this is a massively high-weightage topic. So my goal today is to help you master it efficiently. We're going to visualize the rules, tackle the exceptions, and lock down the core concepts. Let's dive right in.
Here's our roadmap for the explainer. We'll start by mapping out the D and F blocks, then hit configurations and stability rules, the group 12 exclusion, properties and uses, compare lanthanoids and actinoids, and wrap up with some crucial exam practice and a handy checklist.
All right, part 1, mapping the D and F blocks.
Let's start with a quick geographical tour. Think of the periodic table like a massive city map. The D block, that's your vast downtown area, the large middle territory spanning groups 3 through 12. Here, the penultimate d orbitals, the n-1 shell, are progressively filled across 4 long periods. Then you've got the F block. These are the inner transition metals, and they act almost like a secret underground subway system, placed in a separate panel at the very bottom. Down there, it's the deeply buried anti-penultimate, or n-2, 4f, and 5f orbitals that are getting filled up. Now you might be wondering, why do we actually call them transition metals? Well, it's because they literally act as a chemical bridge. Their properties smoothly transition from the highly reactive, electropositive S block on the left, all the way over to the incredibly diverse P block on the right. They are the ultimate chemical bridge.
Moving right along to part 2, configurations and stability rules.
Let's look at the local customs of the D block, specifically their electronic configurations. The general rule of thumb is you fill the 4s orbital before the 3d. You can see this working perfectly for scandium, manganese, and zinc. But hey, look really closely at chromium and copper. They completely break the standard filling rules. And listen, test makers absolutely love to trap you on exactly why this happens.
If we just blindly follow the rules, chromium would be D4 and copper would be D9. But nope, the energy gap between the 3d and 4s orbitals is just so incredibly small that an electron basically shifts over. Chromium steals an s electron to become a half-filled D5, and copper steals one to become a fully filled D10. But why? Well, the real underlying reason for this stability is a little something called exchange energy.
So what is exchange energy? Think of degenerate orbitals like identical empty seats on a bus. Electrons prefer to sit alone with parallel spins first before pairing up. We all remember Hund's rule, right? Well, when they sit like this, they can seamlessly swap places. Every single time they swap, they release exchange energy. The more single occupants with parallel spins, the more swaps can happen, the more energy is lost. Because completely filled or half-filled D subshells totally maximize this exchange energy loss, elements like chromium and copper drop down to a much more stable energy state. And remember, in chemistry, lower energy means greater stability. This is absolutely crucial because ionizing these stabilized atoms, trying to strip an electron away, becomes much harder, which dictates everything from their oxidation states to how they react.
Okay, part 3. The group 12 exclusion.
This right here is a classic technicality that shows up on almost every major chemistry exam. Look at group 12 at the very end of the transition series, zinc, cadmium, and mercury. They literally sit right there in the D block territory, yet IUPAC officially kicks them out of the transition metal club. So why the eviction?
It all comes down to the strict IUPAC definition. To be a true transition metal, you absolutely must have an incomplete D subshell in your neutral state or in a common oxidation state. Zinc, cadmium, and mercury, they're completely full. They rock that D10 configuration no matter what. Because their D orbitals are entirely full and stubbornly stable, they simply don't show the hallmark chemical behaviors of true transition metals. We still study them together just because of where they sit, but technically, they're out.
Let's jump into Section 4, Properties, Trends, and Uses.
So what exactly are those hallmark behaviors of true transition metals? The big structural secret you need to memorize here is orbital protrusion. Unlike s and p orbitals, d orbitals literally stick out further to the atom's periphery. This means they're super interactive and heavily influenced by their chemical surroundings. This peripheral interaction is the exact reason they have variable oxidation states, form those famously vibrant colored ions, and easily snap into complex formations with different ligands.
This protruding nature also perfectly explains their magnetism. If a transition metal has unpaired electrons, it exhibits paramagnetic behavior, meaning it's physically drawn to a magnetic field. But if all the electrons are paired up, Like in our excluded D10 group 12 friends, they are diamagnetic and are actually slightly repelled by magnets. Calculating the magnetic moment based on the number of unpaired electrons is a super common test topic, so make sure you practice that.
But beyond just passing the exam, these properties make transition metals the absolute backbone of human industry. I mean, the 3D metals like iron and copper literally built human civilization. On the heavier end, actinoids like thorium and uranium power modern nuclear reactors. Oh, and here's a great trivia point for exams, mischmetal. It's an alloy of 95% lanthanoids and 5% iron, and it's absolutely crucial for making lighter flints. These elements even act as catalysts in petroleum cracking. They do it all.
All right, let's head to Section 5, comparing lanthanoids and actinoids. Let's dive a bit deeper into that separate panel at the bottom, the inner transition metals, or the F block. When you compare them directly to the D block, things look pretty different. The D block fills the N-1 shell and shows broad similarities across horizontal rows. But the F block fills the deeply buried N-2 shell. Because these F electrons are buried so deep, they don't really participate much in peripheral chemistry. As a result, elements within the lanthanoid series look incredibly similar to one another chemically. In fact, they're so similar that separating them in a lab is notoriously tough. Now, when comparing the two F-block series against each other, lanthanoids versus actinoids, keep this massive high-contrast exam tip in mind. Lanthanoids are super happy sitting at a highly stable +3 oxidation state, and they're mostly non-radioactive. Actinoids, though, total radioactive rule breakers. Their 5F electrons aren't buried quite as deep as the 4F, so they actually participate more in bonding. This results in wildly complex and varying oxidation states across the board. Finally, Section 6, exam practice and our checklist.
Let's pull all this theory together with a classic textbook example. On what grounds can you say scandium is a transition element, but zinc is not? If you see this exact question on your exam, and honestly, you probably will, how do you secure full marks based on what we've just covered?
Well, the answer is just citing that strict IU-PASEQ definition. You clearly state that scandium has an incompletely filled 3d orbital. It's 3d1. Then you state that zinc has a completely filled 3d10 orbital in both its ground state and its oxidized states. Just cite those specific electron configurations on your paper, and boom, you nail the question every single time.
Okay, to make sure you never, ever miss a mark on configurations, use this 5-step mental checklist. First, determine the standard expected configuration. Second, immediately look out for the D4 or D9 trap. Third, if it is D4, shift an S electron to make a stable D5. Fourth, if it's D9, shift an S electron to make a stable D10. And finally, always double-check if the element is in group 12 so you can correctly identify it as non-transitional. Easy, right?
As we wrap up today's explainer, I want to leave you with a bit of a provocative puzzle for next time. We briefly mentioned pore shielding in the F block earlier. If the pore shielding of 4F electrons causes lanthanoid atoms to physically shrink predictably as you move across the row, a phenomenon known as the lanthanoid contraction, how does this essentially force heavier 5D elements like zirconium and hafnium to act as almost identical twins in nature? Ponder that one, keep reviewing these slides, and I will see you in the next explainer.